Okay, off we go. So whoops, I'm on the wrong page. Last time we were talking about how to compute partial derivatives once you've established that one of your variables is a function of the others, right? And in particular, here's the last example we looked at, and we had this surface here, and it's a nightmare of a surface. No idea what it looks like. I can't use any geometric intuition about the surface to answer the question of whether I can view x as a function, even locally. I have no idea, right? But we've got this process. The variable that you want to view as a function, take the partial with respect to that, see if it's not 0 at the point in question. If it's not 0, no problem, right? Okay, so we've already done that. Okay, right. So the question came up of how to take the derivatives of our newfound function, and there is this ugly business right here, but I claim it streamlines very neatly and tidily, even though it violates my own rules. Turns out it's okay in this case. This is a perfectly reasonable diagram to use, and we observe that that path gives rise to this term, and this path gives rise to that term. We can then solve for the partial derivative we're interested in, and we got this, and that's where we left off last time. Okay, so let me talk about the landmine. There is a nasty little landmine here. A lot of students step on. And again, the more I talk about it, the less students step on it. So here we go. Let's talk about this minus sign. Why is there a minus sign there? Let me say that differently. Shouldn't there be no minus sign there? Shouldn't I be able to, for example, notice we've got partial f there and partial f there. Can't I just kind of cancel those? That's how fractions work, right? And then let's see here. The denominator of my numerator is my denominator. Again, fractions and all that. The denominator of my denominator is my numerator, and I gotta tell you, I think this works without the minus sign. So the argument goes. Everybody see the temptation on this? It's alluring. Wow, that really seems like it ought to work. Right? This is absolute nonsense garbage. Absolute nonsense garbage. Please don't be tempted by this. Right? Complete nonsense. Now, why is it nonsense? There's a couple different ways to say this. First of all, again, we write this as a fraction. It's not really a fraction, at least not in the sense that this is a well-defined, meaningful thing independent of the rest of the notation. It just isn't. Right? And in particular, if you were to make sense out of what that thing is, if you were to say, well, this represents how much f changes. Well, it represents how much f changes in a certain scenario. Namely, a scenario where xj is the variable and all the other variables are held constant. This partial f down here, I guess, represents how much f changes, again, I suppose, if you want to think of it that way, but again, in a different scenario where xi is the variable and xj is constant. And all the other variables also constant, right? So these are again not the same thing. They are players in completely different stories, and you just straight up absolutely cannot cancel them. Okay, so please don't make that mistake. The right way to think about this is that we have again, just as a reminder, we have a contribution to the change in f that comes from this path, and we have a contribution to the change in f that comes from this path. These two contributions are not supposed to equal. They're supposed to cancel. Right? They have to add up to 0. They're not equal to each other. They're negatives of each other. And that's why we have this minus sign right there. Okay, so anyway, make sure to be really careful about that. Again, really easy to accidentally forget that minus sign. My advice is that when you are doing when you know you're going to use this formula, you've decided that you're going to write down that, equals, and then you start thinking to yourself, wait a minute, okay, so there's a fraction here, and there's going to be some partial divided by some other partial, and blah, blah, blah. It's so easy to get distracted thinking about the very non-trivial, significant questions of, wait a minute, which partial goes where, and stuff like that. And to accidentally forget this minus sign. It's so easy to do. So my advice, write it down first. Get that onto the page. Establish that you're not going to forget that minus sign. Right? Get it done. And then start to think about, okay, which partial divides by which other partial, and stuff like that. Now, why is this important? Well, let's just think about, just imagine a scenario where, you take a test and you write down exactly this minus the minus sign. Let's suppose you just leave that off. What's a grader going to conclude from this, right? What's a grader going to think? And you got to keep in mind the graders are not mind readers, right? They don't know what you were actually thinking. All they can do is try to infer from what you write. And if you write this, I got to tell you, it looks like you're making the claim that these cancel. It looks like you've got the exact wrong understanding of what's going on with implicit differentiation. It's a really unfortunate look, right? So that's why the minus sign is important. The minus sign is important because it is the only thing that distinguishes your understanding of the ideas from someone who's wildly misguided about the ideas. And it's a mistake to oversimplify this and think that's a sign error. Sign errors are -1. Happens to the best of us, right? Well, that's partly true. Sign errors do happen to the best of us. I'm not above it. Y'all are going to catch me in sign errors. I predict probably more than once in the next, what do we got, 10 weeks left in the semester, something like that, right? We're all susceptible to making inadvertent sign errors, but the question is, why do we make a sign error? If you make a sign error because you had 5 minus signs and you miscounted the 5 and you miscounted the 6, and yeah, that happens to the best of us, right? That's not what this is, right? This really could be that someone doesn't know what's going on, and you don't want to give that really unfortunate appearance. Okay, so big deal. You've been warned. Make sure to write down that minus sign. Let's see an example. Now, y'all are going to recognize this equation. This is the exact equation we looked at previously. Same point, same equation. We've already established that x is locally a function of the other variables, and all we want to know how to do in this question is figure out how to compute that partial. Now, there is a problem here. This question is in terms of x, y, and z. This formula that we would like to apply is not in terms of x, y, and z. Okay, and this is a routine situation. In fact, almost never in practice will your variables actually be called x1 through xn, and specifically you need to know the partial of xi written as such with respect to xj written as such. The odds are just stacked against this scenario, right? So what you want to do is think not about the names of these variables, but think about the roles that these variables are playing, right? And I'll just come out and admit it. My method for remembering this formula is, well, I remember that minus sign, right? That I'm not going to mess that up. I hope. Oh God, I hope, right? Certainly, I'm going to make every effort to remember that minus sign, and then again, full confession. Whatever's there, I'm going to just remember it. Yeah, it looks just like it ought to go there, other than that minus sign we've already discussed. And this thing here, yeah, it really looks like it ought to go there. That's how I remember, honestly, right? So I remember this faux cancellation, this faux argument about how fractions work. It's a bunch of nonsense, but it's a great memory tool. And that's what I'm going to suggest that y'all do. Again, that's what I do. So yeah, when I wrote down this very first thing here, I said, okay, we want to compute that partial derivative. Okay, so that is, and then I step one, write down that minus sign. Again, get that on the page. Don't leave that to chance. Don't trust I'll remember to go back and do that later, right? And then, give me 2 seconds, and then you, just as we described before, the numerator is the denominator of the denominator, and the denominator is the denominator of the numerator. Yes?
I was asking you to just go back a slide for 1 second.
Mm-hmm. Yeah. Yeah. Okay. All right. Okay. Everybody happy with that? Yeah. All right. And now it's just a matter of computing various partials. Let's see here. So I'm going to let you all do the algebra on that. Partial derivatives, that's all easy. You plug in the point in question, right? We're looking at 1, 2, 3, so that gets plugged in. And then all together, the partial derivative we're trying to compute is that. Okay. I have one last comment about all this, and that is, it's another kind of a strategic observation, and that is, how are these questions going to come at you, right? And in practice, they don't come at you like, whoops, I'm in the, oopsie, hang on. They will not come at you like this. This is kind of a weird scenario, frankly. We were asking a question in a context where we had already previously established that x was a function of y and z. We had just got through establishing that, right? And so, as a next example, makes sense to be able to carry that over and use that as a given. That's not how life tends to come at you. Right? So in practice, here's what y'all are going to see, not just in my class, right, but in just kind of in everyday applications of implicit differentiation. That's not going to be given. You're going to have some equation describing either a surface that you're looking at or some known relationship between various variables that are involved with whatever application you're working on, and you're going to find yourself wanting to compute one of these rates of change, right? One of these partial derivatives. And again, that's just going to come up in the situation. The situation will not come with a warning sign that says, hey, by the way, don't forget, before you start going around taking derivatives of things, you have to establish that they are functions, right? That's not going to be there, right? So you have to remember that. That's part of your job as a user of implicit differentiation, to remember that step one is to establish that the thing you want to even apply this formula to actually is a function that you can apply it to. Right? So when you see a question like this, you cannot just write down only this as your answer. That is the second half of what you need to do. What you need to do first is ask that question and resolve it in the affirmative first. Right? This is the first half of the solution of, again, a question as you're realistically going to see it come in. That's the first half. Establish that x is indeed locally a function of y and z. And then second, compute that partial derivative with this formula. You got to do both. Don't say I didn't warn you. Right? And by the way, these are, I called it first half, second half, and that's approximately how they're reflected in the grading. Establishing that it is a function in the first place will typically be about half of the points of a question like this, where you've been asked to compute a partial. Yes?
So you're saying if we're told that x is
yeah, if it's given, then you don't have to establish it, okay. Right? But I'm just saying that's ultra unnatural.
Okay.
Yeah, I mean, I'm not saying it won't happen, and unnatural situations arise, right? But in most of the time, it's just not going to be the case. Okay, so as I have written here, establishing that the thing that you want to take a derivative of is something that you are allowed to take a derivative of. That's really an important part of the solution. So keep that in mind. Okay, that finishes our discussion of Chapter 2, and we move on now to Chapter 3. Well, okay, I mean, we've already done Section 3.1. We did that because I like the results of 3.1 as a handy tool for discussing 2.5. So again, I covered early. We're already done with that. Okay, so 3.2, there's a bunch of stuff in 3.2, some of which is ultra important, and some of which is just a little bit of a digression. It's interesting if we had a load of free time that we could afford, then yeah, sure, but we just don't have the time, and frankly, I'm going to go quickly through all but just this first little bit of 3.2. And a lot of it I'm going to leave to y'all. So, okay, let's do the important stuff first. That's what I have here at the top of the screen. And here we go. So, yeah, we've got a parametric curve, right? Keep in mind a parametric curve position as a function of a parameter, typically t, typically time. And so there's our curve. And let's see here. How would I understand the following question? Suppose I am at some point on my parametric curve, and at that point, let's suppose I know my velocity. How would I linearly estimate the change in my position, right? So I was here, this is my starting point, and I want to make a linear estimate of that point, namely where am I going to be, dt seconds later. Linear estimate, right? We're not going to get the exact answer. We just want the linear estimate. And the linear estimate is a pretty easy argument. I would say, look, I have an actual velocity vector here. There's my x prime vector. And if you know velocity, then my displacement is velocity times time. In fact, let me go ahead and circle this whole thing. Displacement is velocity times time. That's just fundamental. That's the definition of velocity, right? Is displacement per unit time. Okay. So I'm going to call that dx. Now, why do we call it dx? I mean, look, if you like, you could look at this first equation over here and say, yeah, you kind of divide by the dt. Dx over dt is x prime. It seems kind of natural, I suppose. I think there's a better way to think about this. Dx, independent of the notation of derivatives, this just makes sense as it is. X says position. D says differential, namely linear estimate of a change in position. This says linear estimate of my change in position. That's exactly what it is. So dx really makes sense. Now, I spend a minute talking about this because I think it is a little unsettling the very first time you see a differential that's a vector, right? Every differential we've seen previous to now, if I remember correctly, I think they've all been scalars previous to now. It actually makes sense in this context to have a vector differential. Yeah, anyway, mathematically, it's not unnatural, but it is just a little disturbing the very first time you see one. But that's all that means. All right. Okay, next question. Let's talk about how would I estimate. Let's see here. Let me get rid of all of that. How would I estimate the distance that I've traveled? Now I'm going to call that ds, and I'm going to represent that by highlighting this little piece of the curve. So I'm interested again in the sort of how much distance is there along the piece of the curve. And my picture is a little unrepresentative because as I've drawn it here, I've drawn the actual distance along the piece of curve, and that's not what I want. Right? ds is not the actual. Differentials in general are not the actual things that you're estimating. It's the estimate of the thing you're estimating. So what would be my estimate of the length of that little piece of curve? Well, again, appeal here. the dx vector is a vector that's estimating the change in position. Notice that means that the dx vector as an arrow is pretty close to a copy of the little piece of curve itself. So what's my estimate of the length of that little piece of curve? Well, the length of the dx vector, I think, is a pretty natural nomination for how to estimate the length of that little piece of curve. Everybody buying it? Okay. Yep.
So in this case, we say that that's a vector, right?
The what now?
The dx is a vector.
Yeah, that's right. So the dx, yeah, this.
So we just use a normal way of getting the magnitude of vectors, like x squared plus y squared plus z squared plus y.
Oh yeah, magnitude. Yeah. This is the classical magnitude. Absolutely. Yep.
Okay.
Yep. And how we would actually, are you going to compute that for an actual differential? Maybe not. That's not really the point. But yeah, it's the same idea of magnitude.
Okay.
Yep. Totally. Okay, and then of course, by the way, don't forget that dx is x prime d. Well, okay, let me. Dx is v dt. And keeping in mind that dx is v dt, then its magnitude is magnitude of v times dt. So just another way to write morally the same thing. Okay. All right, next thing to talk about. What's the deal with this t vector? The t vector. Okay, so again, keep in mind we're talking about a parametric curve. So we're cruising along here, drawing this parametric curve, and at a given moment I'm here, and I'm moving with a certain velocity. And here's the thing, if you're moving with a certain velocity, among other things, you're moving in a certain direction. How do we represent directions? We do it with unit vectors. Yeah, exactly. So I need a name and a notation for the unit vector pointing in the direction of motion. And I think it's a pretty easy pitch that the way we compute that is to just observe that the velocity is pointing in that direction, and let's just then unitize, right, normalize, divide by its own magnitude the velocity that's pointing in the direction that we're interested in anyway. So take your pick of these two formulas. They're the same formula, of course. That's what we call capital T. This is our unit normal vector. Our unit tangent vector for the parameterization. Everybody happy? Okay. Now that I claim relates to dx. And again, reminder, here's our dx vector. Right? I claim that dx is TDS, and how can you see that dx is TDS? I'm going to give you two ways to do it. If you want to do some algebra, it's actually pretty straightforward. We just got through writing down a formula for t. Here it is. We just got through writing down a formula for ds. There it is. And you literally take the formula for t, the formula for ds, you plug them in, and you're going to get dx. Right? So it just, algebraically, it just fits. It just works. And I encourage you to do that algebra, to just plug in and confirm that, yeah, indeed, it works. Good little exercise. Here's what I think is a better way to think about this, personal preference. Dx being as it is a vector, dx is characterized by a direction and a magnitude. The dx vector, what direction is it pointing? T. What's its magnitude? ds. Done. Of course it's TDS. That's the direction, that's the magnitude, so that's what dx is. I think that's much easier to remember. You're much less likely to screw that up and forget the algebra, or just even easy algebra is easy to mess up here and there. That is conceptually simple, and I think you'd have a hard time forgetting it. Once you really understand that argument, hard to forget it. All right. Okay, so this is the stuff that I wanted to spend the most time on in 3.2. The rest of this stuff is stuff that, yeah, it's okay, true. Yeah, this is stuff we need to at least kind of throw some words at, but this is very algorithmic. It's very plug and chug. You don't need me to explain ideas. There's no deep water in a lot of what's about to come next. Anyway, here we go. How do I compute the total arc length of a parametric curve? And well, that total length is going to come from understanding little pieces of length. Little pieces of length, ds. We just got through agreeing that ds is magnitude of v times dt. And the whole is the sum of the parts. So the total length is the sum of the differential lengths, or in the limit then the integral of the differential lengths. So nice punchline, and the one that's computationally most sort of immediately convenient, that right there, you're just doing an integral of the speed. Yeah.
Are the bounds the 2 points?
One more time.
Are the bounds the point we started at?
Yeah, that's right. So recall, that's right. So when we say we're going to add up all of the actual parts we're interested in, and what we're interested in says right there is t going from a to b, and so our dt integral goes from a to b. Yeah, totally. All right. Okay, so computational plug and chug. This is very straightforward. So you want to compute the length? Okay, well, there's the formula for length. We're just totally going to do exactly that. Apparently, I'm going to need to compute the magnitude. Okay, magnitude, yeah, cool. Of the derivative, right? V is the velocity, that's the derivative. So I am going to have to take this position formula for the parameterized curve, and I am going to have to take its derivative. There. Right, so check me on that, make sure I did that right. Taking the derivative of position to get velocity, which is what that is. And then it's just a matter of writing down the magnitude and trying to figure out how we're going to cope with the fact that this integral stinks. Right, look at that integral. That is terrible. That's a hard integral. And by the way, very often it's worse. Right? I mean, this is the unhappy result of an initial parametric curve that isn't even that bad. Right? So unfortunately, the resulting integrals very often are intractable. You just can't do them. There are a few examples where they turn out to be kind of doable with a little bit of trickery, and I'm going to show you one of those in a few minutes. And there are also other examples where the integrals end up being integrals of constants, and of course those are super easy, right? But there's very few examples where you get the constants. And the vast majority are intractable, or at least major pain. This one, I think this might be doable. I'd have to really do some thinking to remind myself of various tricks that I might be able to pull. I might be able to do a change of variables on that. Anyway, might be doable, but it's certainly not pretty. Okay. So let's talk about the arc length parameterization. I'm going to start with an innocent observation. This is a parameterization of that curve, easily checked. Right? You plug in x, you plug in y, the equation works. Here's the thing. That also is a parameterization of that same curve, isn't it? Right? Because you plug in x, you plug in y, and it works. Okay, so the first thing I want to say about this is don't make the mistake of thinking that there is something called the parameterization of a curve. Not so. There are many parameterizations of any curve. The easiest way to understand this, in my way of thinking, is that keep in mind what a parameterization is. A parameterization is basically literally drawing the curve, right? And there's lots of ways to draw a curve. Right? So as many different ways as there are to draw, you can draw it really fast, or you can draw it very slowly, or you can draw it fast for the first little bit and then slow and then really fast for the last little bit. Whatever, right? So likewise, lots of different parameterizations. Second observation I want to make. This parameterization is arguably what you might call a reparameterization. This is arguably what you get when you take this formula for t and plug it into there and see what comes out. Right? Starting with the parameterization on the left, plug in a formula for t, you get a whole new parameterization. So this is called a reparameterization, reparametrizing the curve. Okay, so it turns out there is a special reparameterization that is very nice, and that is to use distance as the new parameter. So now suppose we have some parametric curve, and here's a point on our parametric curve, and let's talk about how I can describe that point on my parametric curve. I could view that as that's the point that I'm at time t. That'd be one way to describe that point. Here's another way to describe that point. I could say that's the point that I'm at after I've gone s miles. Right? So I could describe it by time, or I could describe it by distance. And by the way, an easy little metaphor for this, imagine a road trip. By the way, think it through, right? If you're driving on a road in your car, as you drive along the road, you are parametrizing that road. Because you're literally, the position of your car is tracing out the path that that road follows. You know what I mean? Right? Okay, so every time you take a road trip, you're parametrizing the road. And okay, well, fine. So you can document your location as you drive by, looking at your phone, and maybe you have a phone, maybe you have an app that shows you longitude, latitude, whatever, right? And every minute you make my location is blah at 3:52 p.m. My location is blah. And then at 3:53, you note your location. And at 3:54, you note your location. You keep track of all your locations as functions of time. Perfectly fine, perfectly reasonable. That is a way to parameterize. You could also use your odometer, though. Right? The thing that measures the distance that you've driven, right? And so you could say, right at 17,468 miles, I was at this spot, and at 17,469, I was at this spot, and at 17,470, I was at that spot, and just document your location by distance traveled according to your odometer instead of time elapsed according to your wristwatch. Okay, right. So these are two different ways to parameterize the exact same curve. Okay, so notice conveniently, I can solve for s as a function of t. You give me some time t, and you want to know how much distance is traveled? Well, on the previous page, there you go. There's your formula for distance. Right? At a certain time, traveled between time 0 and time t. And if you know s is a function of t, you can hopefully, theoretically anyway, solve for t. And if you take this t, if you solve for that t and plug it into there, then you would get position as a function of s. And this is what we call the arc length parameterization, or reparametrizing by arc length. That's all it is, yes.
Is there a reason you're using tau?
Yeah, it's an annoying little sort of, it's what we call a dummy variable, right? If you think about it, anytime you write down an integral, this is just a placeholder. This is just saying that, look, I've got this expression, and I'm going to be putting different numbers into this integrand expression and, adding up according to the Riemann sum, rules, right? So what do I call that thing? It's going to take all the values between here and here. And the problem is, t is the upper bound of my range. So the dummy variable that goes over the entire range, I can't call it t because I've already called this other thing t. So I just need a different dummy variable. I could have called it q, I could have called it w, I could have called it bob. Doesn't matter.
But is it not with respect to this?
I'm sorry?
It's not the same. So it's not the same t?
It's not the same t because t is fixed as I compute distance. Right? As I compute distance, I've got to sort of move along this entire part of the curve. T represents where I am at the very end of this little piece of curve. So t cannot simultaneously be at the end and immobile and also ranging over all these values.
So those, you're saying the tau is kind of like the coordinate system.
The tau is it's just a different dummy variable. Yeah. Right. So I mean, look, if I were to ask you what's the integral from 0 to 1 of x dx, you compute and you get some value. And if I were to ask you, oh yeah, but what's the integral from 0 to 1 of q dq? It's the exact same calculation. And what the variable name is called doesn't matter, right? It's literally why we call it a dummy variables, because it's completely irrelevant. It's just a placeholder.
Okay.
It's not actually relevant to the question. It's just a tool that I use to compute something relevant to the question.
Okay. So you're taking the x prime with respect, or using the tau variable.
Yeah.
And then
Tau is
integrating for tau.
Yeah, I mean
And
integrating
then
with respect to tau. Yeah, just to represent sort of moving along that whole piece of curve.
Okay,
Yeah.
got it.
Yeah. Okay. All right, so that's what an arc length parameterization is. Why do we care about it? It turns out it's nice for certain purposes that we're actually not going to use very much. Yes, question.
About the earlier thing,
Yeah.
are we always going to be given x of t, or can we derive it somehow?
Oh, every question's different. I don't know. I don't know what.
Is this only going to work if we are like explicitly given the formula for x?
This technically all I really need is x prime.
Or like x prime.
Yeah, I can't answer questions about will I always, because I don't know what I'm going to do. But this is the formula, right? Now how you would make use of this, I don't know. It's going to depend on the context, and I don't know, right? But this is what we need to compute distance as a function of time.
Yeah, I guess what I'm more asking is whether the x can be derived using any of the equations we were just talking about.
I'm sorry, I don't understand.
Okay, I'll
Okay, yeah, that'd be fine. That's totally fine. Yeah. Okay. So why do we care about arc length parameterizations? My first observation is it is intrinsic to the curve. And let's go back to the road trip metaphor, right? And let's think about, if you were to write down a parameterization based on time, and again, you're just going to look at your watch, and every time you get to a minute, you write down your location, and you just keep going throughout your whole road trip. Well, if you drive faster, then you're going to have one parameterization. If you drive slower, you're going to have a completely different sheet of noted locations at different times, because you drove faster or slower or whatever. Clearly, it's going to depend on time. But if you're writing down your locations by way of distance, it doesn't matter how fast you drove to get there. Whether you drive fast or slow, having driven exactly 12 miles will always put you in exactly the same spot. It only depends on the road. It doesn't depend on the driver. Does that make sense to everybody? 12 miles is 12 miles, no matter how slow, no matter how fast. Right? So something being intrinsic to the curve itself and not depending on arbitrary, meaningless stuff such as how fast I personally drive my car, right, is a good thing. We like things that are natural and intrinsic, and arc length parameterization is intrinsic to the curve. So that's already cool. The next observation I'll make is that it is what we call a unit speed parameterization. So y'all will notice this is just a chain rule, and here I just take the magnitude of both sides to give me that. And kind of a cool observation to just kind of notice is, check it out, this and that are the same. Yeah, you got to think it through. What is dx dt? Oh, x is position, dx dt is velocity. This then on the left is the magnitude of the velocity, which is the speed. This on the right, distance per unit time, also speed. Right? So these two things are both speed, and therefore they're the same, and therefore they cancel, and therefore this thing is 1. And that's what we mean by saying that this is a unit speed parameterization. The derivative of position with respect to distance, not time, distance, is always a unit vector. So that's kind of cool. And that has some nice consequences when you're proving certain theorems and stuff like that we're not really going to do in this class. But again, tragically, ugly integrals tend to happen. Okay. So here is an example of this. Here is a parameterization. The question says we want to find the arc length parameterization. So we're going to reparameterize by arc length. Of course, in order to do that, I need to compute arc length. Right? S is a function of t. And that means I got to use this formula, and there's going to be a magnitude, which is a square root, and you can see it gets a little ugly, at least in the middle there. Okay, now I pulled a fast one here. I carefully, just so, crafted a parameterization that when you take the derivative, and then you look at these components of the derivative, and you square and add, check it out, squaring and adding leaves me with something that happens to be exactly a perfect square. Right? And that doesn't happen super often. But by the way, this, I saw, I'm going to say morally equivalent to this example, I don't know, a dozen times in my undergraduate physics major. This is not unheard of, this kind of thing. There are lots of natural scenarios where this kind of thing really does happen. So you want to make sure to be on the lookout for it. That's why I have this example in here, frankly, is because I want you all to be on the lookout for this phenomenon where you have one square, right, where you notice this conspicuous minus sign, and then the other square is exactly what you need to turn that minus into a plus. So it turns one perfect square into a different perfect square. Right? And again, I saw that a dozen times in my undergraduate physics major, and I suspect y'all will see it at least a half a dozen times in your engineering majors. I think most of y'all are engineers. Right? Okay. All right, so heads up on that. Okay, so carefully I arranged to get one where you could actually work out the integral, and then here's the anticlimactic punchline. Great, I was able to do the integral. Now let's solve for t. Oh, boo, I can't. Right? So the algebra on these regularly stinks. The only examples that I'm aware of, let me not overstate, basically the only examples I'm aware of where this is algebraically doable are situations where the integrand ends up being a constant. And I think there's at least one homework exercise where that's going to happen. You're going to find the integrand's a constant, and so this is a linear relationship, and then it's very easy to solve for t. So anyway, heads up. Okay. All right. Okay, moving along. Let's see how we do. Oh, we got a minute. Okay. Okay, 3.3, we're going to talk about vector fields a little bit. This is a new object of interest. This is going to be, by the way, one of our primary objects of interest in chapters 6 and 7. So when we get to what is sometimes called vector calculus, and there's some really powerful ideas in vector calculus. Arguably, all of vector calculus is just, hey, what's the calculus of vector fields? Right? So remember, we've talked about the calculus of graphs. We've talked about the calculus of level sets, calculus of parameterizations. We're going to be talking about the calculus of vector fields. And I'm going to remind you, they all look different because they're all different constructions, right? They're all different kinds of pictures that we draw for various different reasons because there's so many different circumstances, and sometimes I can't draw the graph. And sometimes I can't draw, well, I guess I could, but level sets have their own disadvantages. And vector fields are just another kind of function that serves a very specific purpose, and graphs just won't cut it. Level sets won't cut it, etc. So, okay, so we need to understand what vector fields are first, and a vector field on Rn is a function that fits this form here, namely its domain is Rn and its target is Rn. But there's really more to it. A vector field is one of those kinds of functions where you take a very specific perspective on how to think about the inputs and how to think about the outputs. So specifically, we're going to think about the inputs as points, and we're going to think about the outputs as vectors. And now wait a second, how do we draw vectors? We draw vectors with arrows. Okay, well, yeah, but where do I put the arrow? We represent these output vectors with arrows that have their tail at the given input point. Now, that's an arbitrary set of rules, right? We view the inputs as points, the outputs as vectors, represented by arrows with their tails at the given point. That's what we mean when we say a vector field. Everybody good? Okay. So you get pictures like this, and first observation I'm going to make is this is actually really natural stuff. I mean, I don't know about y'all, but when I see this picture, I think, oh, man, it's like there's a fluid. It's like there's a fluid just kind of flowing that way, right? It's just almost like you can just imagine each one of these arrows represents like maybe a velocity or something. And when you're here, the fluid's going that way. When you're here, the fluid's going that way, and stuff like that. This really looks like how fluids flow. And in fact, vector fields are the perfect construction for describing the flow of a fluid. They're exactly what we need to describe the flow of a fluid, and that is something that we're going to need to do. And so this is how we're going to do it. By the way, here's another totally different physical scenario for which vector fields are the perfect tool, and that is force fields. So gravitational fields, for example. Think about it. Wherever you are, there is a corresponding force, and forces are represented with vectors. So for every point, there's a vector, just like we have here. Right? So lots of real-world scenarios where vector fields are the perfect tools. Let's see. So there was one other comment I want. Oh yeah, I've kind of already said this, but let me just finish with this one last thought. You do have to make a conscious point of not kind of blurring the lines between these different kinds of pictures that we draw to represent different kinds of functions. Right? So we draw graphs for, convenience in certain ways, and when you know you're looking at a graph, calculus manifests in certain geometric ways. If you're looking at level sets, it's all different. Right? The geometric interpretations are all different. So the calculus of graphs, not to be conflated with the calculus of level sets. Not to be conflated with the calculus of parametric curves, and not to be conflated with the calculus of vector fields. So we're not going to look at something like this and try to imagine that, I guess, in some way the derivative of one of these, some kind of a derivative maybe would tell me the slope. Don't derivatives tell us slopes? No, that's with graphs. This is not a graph. Right? So completely different geometric interpretations. And just to put the emphasis on how out of hand this is getting, right? How many different kinds of pictures do we have at this point? We have graphs, level sets, parameterizations. There's that, what I like to call the literal picture. Those are all different. This is now number 5, right? Type of geometric construction number 5 in this course, and I think this is it, by the way. But anyway, lots of things that you have to make sure to keep distinct in your mind for stuff to make sense. Okay, so that's out of time. We'll draw the line right here. See y'all on Friday. Whoops. derivatives.